All right, good afternoon, everyone. We are in section 8.3. Actually, we're skipping 8.2 for a second. 8.3 is confidence interval for a difference of proportions. So in 8.1, we spent some time looking at how to build a confidence interval for a single proportion, but now we want to say, hey, what if we want to compare two different populations and the number of proportion of successes? All right. So some just terminology first. P1 hat is population one, so it's the proportion of successes in a sample of size N1. So you'll see N1 in there for the population one. P2 hat is the proportion of successes in a sample of size N. N1, N2, sorry, N2. Sometimes they're the same, often they're the same, but they don't have to be the same actually. So conditions, just like the last round, we have to meet certain conditions to be able to use the normal stuff that we're using. There's basically the same ideas. First of all, remember last time we had to have a simple random sample. This time we have to have two independent simple random samples. All right, so the populations need to be independent. The second thing is each population needs to be at least 10 times as large as its sample size. Same condition as the other one, right? But this is for two different populations. And then this is basically the same thing also. Sorry, a little typo there. N1 P1 hat, N1 Q1 hat, N2 P2 hat, N2 Q2 hat. So the individual ones for each one all have to be greater than or equal to 10. It's basically saying the sample size is big enough. That's the whole idea of all of these, right? Is that we have a big enough sample size. And then if so, there's just another formula. So here's the confidence interval for the difference of proportions. So you take those two proportions and you subtract them. P1 hat minus P2 hat, that's the center of your confidence interval, plus or minus some critical value again. I put a star on there, Z star. We'll talk about Z star more in section 2. So that's why it's a little bit weird that I jumped to 3, but it's a more natural jump because this section is very much the same. And then you're basically adding the two variances together. Remember about sampling distributions. Remember the standard deviation for each one of these is PQ over N, right? So if I put some ones on here, P1, Q1, N1, square it, that becomes the variance. P1, Q1 over N1, that's what this is, right? Oh, that should be N1. Sorry about that. And then N2. So you add the variances together, take the square. It's the same exact standard error as it was from the last section 5. So the formula is just a little harder to work with because we got a little bit more calculator punching, but it's not too bad. So we're just going to do an example. It's a pretty straightforward section. Falls right through, and then interpretation. So in 2001, 45% of 1,016 houses owned a dog. In 1996, 43% of the 1,016 houses owned. So these are both two independent simple random samples. Okay. So the question is, what is the change in percent of owning a dog? So find a confidence interval for the difference of proportions is what we're trying to find. Okay. And again, just a little reminder of the formula, and I'll put this standard error in here, P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2. All right, so we got 45%. So my P1 hat minus P2 hat is 0.02. That's the 45 minus the 43. You can subtract the other way, by the way. You could say negative 0.02. I'll show you that at the end. It's not going to matter. Your confidence interval is going to be backwards, but when you word it the right way, when you just say the difference. So I just subtracted 2001 from 1996. But you could do it the other way. No one's saying which way to subtract it. Plus or minus. We'll do 95%. I didn't write it in there. The same deal goes for the Z's, whatever confidence level you're using. So I'm going to go 1.96, and that'll be the square root of. So it's 0.45 times 0.55 over 1,016 plus, that's the first population, 0.43 times 0.57 over the second population. Give me a second while I punch my calculator. It's 1.96 times the square root of 0.45 times 0.55 divided by 1016 plus 0.43 times 0.57 divided by 1016, 0.043%. So again, if we're writing percent, it's 2% plus or minus 4.3%. Or you could write that as negative 2.3% to 6.3%. Okay. If you subtracted the other way, you'd have negative 0.02 or negative 2%. plus or minus 4.3%, which would get you from negative 6.3% to 2.3%. So notice they're just opposite. Everything's flip-flopped. So I would say I am 95% sure that the difference in population proportions of people who own a dog, people who own a dog between, sorry about the wording here, sometimes the wording gets over 2001 and 1996, 96 is somewhere between. So now I told you what I just told you was which way I subtracted, right? I'm 95% sure the difference population reports of people who own a dog between 2001 and 1996, so I'm subtracting that way, is somewhere between negative 2.3% to 6.3%. If I said I'm 95% sure that the actual population proportion of people who own a dog between 1996 and 2001, then I would switch those proportions around. All right. And one last thing to look at. That's it. That's all there is to it. It's just an application of a formula. I have another example, but there's not another reason to do another example. You can just kind of look at this one again. But there's one last thing I do want to say, and that's something. What was it? Oh, yeah. Often the question that might be asked now, is there a difference or is there evidence of a difference? So we're going to talk about this when we go back to section 8.2. Notice that 0 is in that confidence interval, 0%. So what that means is we're not really sure there's an actual difference. This would be like a presidential election thing also, again, right? Like if these are your differences, there's no difference. It could fall anywhere from negative to positive, which means either guy could win in essence, right? If this interval was from like 5% to 10%, then you would say, yeah, there is evidence of a change. But because 0's in there, 0 in interval, there's no evidence of a change. Okay. We'll talk a little bit more about that. We'll do hypothesis testing in section 8.2. So that's it for 8.3. We'll see you in class.